we're going to have to derate the battery packs that go into aircraft so that you have consistent available performance from the day one that it goes into a service until you retire that battery pack. Because it's not okay to say, okay, I've got a Cessna 172 and it went out the door with 50 gallons of fuel, but every 3 months that shrinks by 1.5 gallons. And, we just wouldn't deal with that for flight planning. That's not good for safety.
Welcome to Hangar X Studios, where former fighter pilot and host John Ramstead takes us on a journey across aerospace as it enters an historic period of innovation and transformation. Our guests include aviation experts, pilots, financiers, military leaders, and innovators of all types. Buckle up for another episode of Hangar X.
Hey, this is John Ramstead, and welcome to the Hangar X podcast. And today, we're going to be exploring a very critical area in this entire space of aviation and advanced air mobility, regional air mobility, and that is propulsion. And I don't know if you guys know this, but there's almost 600 companies developing some kind of electric vehicle, eVTOL, UAS, drone that needs a propulsion system, and can electric take care of it? And that is what we're going to be talking about today with the CEO of VerdeGo, Eric Bartsch. Eric, welcome to the podcast.
Thank you. Glad to be here.
So VerdeGo is a pioneer in hybrid electric propulsion. And we're going to be talking today about some of the limitations of battery and battery technology and where VerdeGo saw a need in the market. And I know a number of people we've brought on when you're looking at longer range missions, shorter range missions, cargo. There's a lot of advantages to electric, but there's also a lot of limitations to that also. So
definitely.
Eric, if you could just share maybe a little bit about your background and what VerdeGo was done and founded to do, and then I want to really get into some of the details. One of the things you've recently developed is a hybrid electric engine with megawatt level power that opens up some pretty interesting possibilities. But with that, let me turn it over to you.
Thank you. Yeah, so VerdeGo Aero, we founded the company in 2017, and the three co-founders, all of us, we had been in the early stages of the electric flight industry in various different programs. We'd seen the potential in the years prior to forming VerdeGo, and all three of us came to the same conclusion that there are some really compelling things about electrifying an aircraft, and that is the future for many of the segments of aviation. That's the reason why there are more than 600 programs going after electrified aircraft and drones. But we also realize it's not going to play out the way people necessarily expected, and it's certainly not going to play out the way it does in the automotive industry. And so, you think about the beginning of any innovative company, there's usually an aha moment where you see the inevitable future. You see ahead of where the market is and where things are going and where you need to get to. And what we realized is that the transformative technology that makes electric flight interesting isn't batteries, it's electric motors. Electric motors are really interesting when it comes to designing an aircraft because they scale differently, they're really simple, they're really reliable, they're lightweight, and as a result, if you think about the history of aviation, generally speaking, for several decades, there are only two answers to how many engines there should be on an aircraft. If it needs commercial redundancy, it needs two. If it doesn't need commercial redundancy, it needs one. If it has less than one, it's a glider. If it has more than two, it's inefficient. So aerospace engineers have been boxed into a corner of having one or two propulsion systems for many decades on the vast majority of aircraft programs. The big thing that electric motors do is they allow you to have a lot of points of propulsion on an aircraft if you want to, and they allow you to really precisely and rapidly vary the propulsion at those points. If you want to start controlling the airflow over the whole aircraft and not just at 2 points under the wing, you can do that. And so if you think about all of these kind of crazy looking things that have emerged in electric aviation, all these urban air mobility, air taxis, flying cars, some of the drones, those of us that have been in aerospace for decades initially looked at those and said, those kind of look crazy. That's not what an airplane's supposed to look like.
Well, and the answer is, it's not really an airplane. That we're developing a whole new category, right?
Exactly. And so
an airplane as we knew it. How's that?
Exactly. And so, we all knew what a piston engine airplane should look like. We all know what a jet airplane looked like. None of us really knew what an electric airplane should look like. And so we realized that was going to be really compelling. It was going to be driven. The electric motor is the driving technology that makes it all really exciting. And what was inevitable was that batteries aren't moving fast enough to make a lot of the missions that we really want to use these aircraft for viable. So how do you make that practical? Well, that's where you get into hybrid electric power and generating power on board the aircraft so that you can make these new types of aircraft highly capable and compelling, and you can get beyond the limitations of just using batteries alone.
That makes sense. As I think about the propulsion system you had when I was looking at, how it provides the electric side, because if I had a normal, conventional engine, I have to have a transmission and a way to get the power to a gearbox to actually turn that rotor.
Right.
But when you're talking about an electric motor, I just got to make sure it's wired to a source. It's very different. It's a little more straightforward, correct?
Absolutely, and it's great that you went there because, as I said, electric motors are the most compelling thing that makes us want to electrify aircraft. The second thing down the list is electric power distribution. And if you think about aircraft that want to have convertible flight modes, talk about the V-22 Osprey for a minute. That's an amazing airplane. I mean, it can behave like a helicopter. It can behave like an airplane. It moves faster than any helicopter. It lands vertically like a helicopter, though. But the mechanical complexity of the drive shafts and the gearboxes and all of those things to link all of the two propulsion units on the wingtips together, that's a whole lot of weight and a whole lot of mechanical complexity and a whole lot of reliability challenges.
And a whole lot of maintenance per flight hour.
Absolutely. And if you think about the simplicity of wires, the easiest way to move energy around on an aircraft is to wire up an electrical bus and move power anywhere you want it to go. And so that combination of electric motors, which are number one, and then electric power distribution, number two, that's what opens this whole array of new types of aircraft to be built by aerospace engineers. And again, that's then why we exist, is to make those really, really capable and practical.
Yeah, and Eric, what was the original design idea when you started VerdeGo Aero that led to what you have now?
So we started out thinking about potentially designing our own aircraft. At the point that we came into the market back in 2017, that was in the early days of the Uber Elevate initiative. That was when massive amounts of funding were flowing into the next generation aerospace market, and that's when a lot of those 600 companies you mentioned got kicked off. And so we came in always thinking about hybrids, but initially thinking about, okay, we can design an airplane that benefits from this hybrid electric power revolution and deliver something that's better than what anyone else is working on. And what we realized pretty quickly is that our true innovation and our novelty was the hybrid power plants themselves. And we decided that rather than design our system for one aircraft that we were also working on, the best use of our innovations was to take those and sell those broadly to many different aircraft and drone manufacturers so that we can really power that whole array of aircraft and that whole wave of innovation.
And you guys ended up choosing turbines, turbofan. There's different ways to utilize the different pieces of this hybrid. Did you consider anything else beside, a turbine engine? And I know everything you're looking at will burn sustainable aviation fuel, but what other options went through the process?
So we looked at a wide array of engines and to really figure out what made the most sense to hybridize, because not every turbine and not every piston engine makes sense in a hybrid electric configuration. They weren't necessarily originally designed for that. And so one of the things we had to get really good at is understanding what is it that makes an engine good for hybridization? What is it that makes an engine bad for hybridization? And so we sifted through a lot of different power plants to come up with the turbines that we're now using on our larger systems, and then the piston engines, the jet fuel powered piston engines that we're using on the smaller scale systems.
Would you consider that a diesel engine?
They're diesel engines. The reason I avoid using the word diesel is they run on jet fuel. So it is a diesel cycle engine that runs on that thermodynamic cycle, but they're optimized to run jet fuel so that they can be easily integrated with the fuel supply chains that the military or civilian aviation.
So, we're familiar with that because I know like the DA-62, which I've flown, has that kind of engine. It has a FADEC controlling. I mean, you start it with the push of a button. The thing is bulletproof. It's efficient. And it's also, in general aviation, is a path to get away from leaded fuels also. So there's a lot of real benefits to this approach. But now you couple this with something in the engine that generates the power, goes into the power grid, charges the batteries. Can you guys talk a little bit, I think, about that approach and how you actually put these pieces together?
Absolutely. So it's interesting because you could write a book hundreds of pages long on all the different ways you can configure a hybrid electric system, because the components are kind of like Legos. You get a few Legos and you can put them together in any number of ways that you want to configure them. But generally speaking, in a hybrid powertrain, you think about upstream and downstream sections of that powertrain. And what that means is...
define upstream and downstream
I'll define
for
it.
all of us non-engine
Absolutely.
propulsion people.
So the upstream portion of that powertrain is where the electricity comes from. So you've got hybrid power generators and fuel tanks that fuel those, battery packs that are integrated with those. So that's your sources of electricity. The downstream end is the array of propulsion motors that could be all over the aircraft, lifting the aircraft, pushing the aircraft, tilt rotors, you name it, whatever those are. And what we figured out, one of our insights early on in forming the company, and one of the reasons we pivoted from being an airplane company to a propulsion company, is that we realized there was going to be a lot of standardization on the upstream end of the powertrain, while there's not necessarily a lot of standardization on the downstream end. And therefore, just like there are, several common sizes of engines, you've got 300 horsepower piston power plants, and there are Bonanzas, Cirruses, Cessna 206s, all kinds of things that are designed around that size. You've got the Pratt & Whitney PT6. That's kind of the ubiquitous turboprop. It can go in King Airs, Caravans, Pilatuses, all kinds of things, even helicopters.
Yep.
You realize that the commonality was that upstream end, and that similar sized aircraft, even if they look different, they're going to need about the same amount of power. And therefore, if you design, for example, our VH4T, which is our most mature power plant now, delivers 400 kilowatts continuous. That's about 550 horsepower of electricity. There are a lot of aircraft that are in development right now, and a lot of drones in development right now, where that's the right amount of power for you. So we can have a common upstream element that we sell to, manned aircraft manufacturers, vertical lift aircraft, drones, urban air mobility, air taxis, things like that. If they're all the same size and they all need about 550 horsepower of electricity continuous, that power plant is the perfect solution for all of those. And then on the downstream end of those powertrains, that's where some of those may have 8 rotors, 6 rotors, 10 rotors, 8 lift and 2 push, all kinds of different configurations. And that's really about the innovations at the airframe level and what our customers are doing that's unique about their aircraft configuration. So we focus on the common elements on the upstream. We let our customers then have the ability to focus all of their powertrain efforts on the things that really make their aircraft unique, and they don't have to worry about the more standard elements and make their program any more complex than it has to be.
Yeah, and I know if people go to your website and look at what you have, I would almost describe it as like small, medium, and large as far as engine solutions. Yep. Have you found certain segments in the market that this is just a phenomenal fit, or are there aircraft platforms that you're designing toward, like some of the ones that are more regional mobility, right? 100 to 700 miles have a very different power requirement than maybe a drone that's going to carry 200 pounds of cargo for 50 miles. But I'd love to hear your thoughts on what you're seeing in the industry as far as need.
So that 400 kilowatt level that I was talking about a moment ago, that is very useful across multiple market segments. And the ones that come to mind are, first of all of the urban air mobility aircraft. These, what I would describe as the next generation of the helicopter, quieter, more efficient, more redundancy in the vertical lift system. The vast majority of those are designed to have 5 or 6 seats right now. And that's an ideal size for that 400 kilowatt power plant. The other thing that's ideal for that is that there are a bunch of drones being considered for both commercial and military use, where they're designing around, let's say, 1,000 pounds of payload, and they want to do vertical lift and then cruise on a wing. And that same 400 kilowatt class of power plant is ideal for that. And then in some of the fixed wing applications, something up to, let's say, 9 to 12 seats on a fixed wing aircraft, you can do a lot with 400 kilowatts of steady state power in that market. For the regional air mobility market, where you're using runways, but let's say we're utilizing underused airports that currently don't have commercial flying going in and out of them. So that's an example where that one power plant size fits many different market segments in ways that really enable those aircraft to be more compelling.
Yeah, and if let's say I'm designing and I'm looking at the weight of different engines, capabilities. From a design perspective, what does the hybrid power plant give me that battery, exclusively electrification does or does not?
It's a great question, and the best way to think about that is I'm going to talk about weight for a moment. And so some of these next generation vertical lift aircraft have, somewhere approaching 2,000 pounds of batteries on board. And that's for a relatively limited amount of flight time. You're probably talking about, mission capabilities of under a half hour, maybe significantly under a half hour if you have to factor in the reserves.
And if we translate that into range, I'm guessing 60 to 100 miles.
Or maybe even less than that, maybe 30 to 50 in some cases.
Especially if you take into account that I need certain reserves with the new FAA requirements, that my effective range could be 30 to 50 miles with 2,000 pounds of batteries. That's what you're saying?
Exactly.
And I'm always taking off at max gross weight.
Exactly, because batteries don't get any lighter, whether they're full or empty. It's the same battery pack. So if you take that battery pack out, take that 2,000 pounds of batteries out, those aircraft that are under development are really interesting aircraft. They are the next generation of the helicopter in many cases. They're going to be better in many ways. But pull that 2,000 pounds out, and that 400 kilowatt class hybrid power plant, that's a 550 pound unit that generates that power. If you take that and put it back in the aircraft, if you take a smaller battery pack, because a hybrid electric system to really be optimized, you do want a battery pack in the aircraft, but it's in there for different reasons. It really takes the transient loads off of the engine that's doing the power generation. So let's say you put 200 pounds of battery back in the aircraft instead of 2,000 pounds of battery back in the aircraft. And then let's say you put a few hundred pounds of fuel in the aircraft. And that's a choice, how much fuel do you want to put on board the aircraft? Because the fuel is more than 20 times more energy dense than the best batteries on the market, what you get there is a powertrain that replaces that 2,000-pound battery, but all of a sudden you've taken the range up 8 to 10 times. You're instead of talking about dozens of miles, you're talking about hundreds of miles of range. You've got no problem dealing with FAA, VFR, IFR reserves. And you can move faster in most cases because a lot of the electric aircraft, because they're energy starved, if they're powered by batteries, they've got to basically fly at their best efficiency speed to get the most out of the charge in that battery. And as you well know, the best L over D speed or the best glide speed for an aircraft is way below the typical cruise speed.
Yes, very much so.
These electrified aircraft could move a lot faster through the air and be a lot more interesting for transportation for longer distances if they just had the energy on board to power it at that level. So you put the hybrid on board.
It's not a linear relationship either.
It's not.
If I'm going to go at 100 knots versus 150, I don't burn 50% more energy. I actually might double my energy requirement. So then I might get there faster, but now my range is reduced. So there's a lot of factors I've taken into account.
Exactly. So if you put in that hybrid powertrain, which is our hybrid power plant, plus a smaller battery, plus the fuel, what you get is much longer range, faster cruise speed, and added payload. And you may actually take that aircraft that was designed as a 6-seater, and all of a sudden you can make an 8-seat fuselage on that and add 2 extra paying passengers. From an operating economics...
Because you freed up 1,000 pounds, and that's significant.
Absolutely, absolutely. So, that's really exciting. So, that's just one example, and there are parallel examples for fixed-wing aircraft, for drones, and all of those things. But you're often talking about way more range, more cruise speed, and more payload all at the same time. And you're doing that in an aircraft that's already been designed to be more efficient than legacy aircraft because it's designed around electric motors and electric power distribution.
Do you think, maybe this is a little controversial, but, with the current state of propulsion and technology, are meaningful commercial missions even achievable with current electrification technology?
So, and I guess I consider hybrid to be one branch of electrification. So,
okay. How about pure battery then versus pure battery?
Got it. Okay. Pure battery, I would say most of the missions that are most compelling and most important for aviation, the answer is no. Because we're off by a factor of more than 20. And the Moore's law for batteries is that they're getting better in energy density 3 to 5% a year. So we're talking decades to get any kind of meaningful improvement. And we don't just need a meaningful improvement, we need a transformational improvement.
Well, yeah, you actually look at the law of 72. That means that 20 to 25 years just to double, and just doubling is probably not going to solve the problem. Unless there's a significant breakthrough in new battery technology, which I know some people are working on. DARPA's working on it, but nothing is commercial. It's a decade away from being commercial, from my understanding.
Right. And so I would say for the next, let's say 2, 3, 4 decades, it's unlikely that we will see batteries that can support the most important missions that we fly with aircraft. Now, that doesn't mean that there aren't niche cases where batteries are usable. I mean, you've got the Pipistrel Alpha Electro that can be used for flight training. You've got some of the very small light aircraft. So there will be battery electric aircraft But the biggest and most important markets are going to have to be hybrid electric, because that's really where you get the performance that's useful.
So I'd love for you to kind of go into engineering mode a little bit, Eric,
Yep.
and just talk about, let's say I'm considering one of your power plants.
Okay.
How does it actually work practically between the turbine, the propulsion that might be available from the turbine side, whether I
Right.
ramp that up or down? How do I harness some of that? Because that has the ability to provide propulsion lift, but then also it's combined to a generator that's powering either my electrical system for distribution or to the battery. But kind of talk about the mechanics of how it works and how some of your customers and OEMs that you're working with are implementing this.
Yep. So I think where I'll start out on that, because it's an expansive question,
It is.
and I want to give you and your audience a good, clear answer. There are two major families of applications of hybridization. One's called series and one's called parallel. What a series hybrid is that's a series of things that are happening with the energy. So you generate the power, you output that power on electrical cables, you run that around the aircraft into electric motors, and you convert that back into thrust. So those are all in series with each other. A parallel hybrid is one where you're driving a main rotor or a main propeller on the aircraft, and that shaft that drives the propeller has both a combustion engine and an electric motor on the same shaft. So in that case, you could run the turbine engine and then augment that with the electric motor. You could run just the turbine engine, you could run just the electric motor, and you've got a whole bunch of different flight modes. And so that's really a decision at the aircraft designer level as to what they want that architecture of the powertrain to be like. And most of the vertical lift aircraft out there and drones out there with lots of propulsion units are using series hybrid because they have so many motors that, there's not really one main thing you can put a drive shaft to. But there are certain applications where there is a main propeller that's pushing the aircraft in cruise, or there's a main rotor that's lifting the aircraft off the ground vertically. And in those applications, sometimes it makes sense to have a parallel approach where there's a mechanical connection between that turbine and that motor generator and the main propulsion.
So thank you for answering that. And it just made me think of, as you're designing and developing this, certification. It's something that all of us have to think about, because in this industry, we don't get to sell a beta. We don't get to sell a minimally viable product. It has to be certified. Either it's alpha or we don't sell it. So what have you guys encountered with the FAA or the process of getting your power plant certified?
So we've been working with the FAA closely for multiple years now. In fact, probably approaching 3 years, I'm thinking. And that's been a very productive process. And they're working with us. They're working with, the other companies. There are a handful of us that are working on various architectures for hybrid electric systems. And frankly, they're excited about that because this is a way to get a lot of the electric, the battery electric aircraft programs out of an area where they may be stuck, where you've got a great aircraft, but you've got challenges with the operational regulations, not necessarily the certification regulations, but as you well know as a pilot, we have fuel reserve or energy reserve requirements, whether it's an airplane or a helicopter, and whether it's VFR or IFR conditions, and whether it's Part 135 or 121 or all of those things. We need reserve energy on board for safety, because not everything goes according to plan when you leave the ground, and sometimes you have to divert around weather, around traffic, closed runways, all of those things. There are a lot of reasons why we all as pilots don't always end up where we intended to be, and that can't be a crisis for the aircraft. That has to be a normal, plannable process that you can easily adapt to. one of the big challenges with the battery electric aircraft, it isn't so much the certification of the aircraft, it's complying with the operational requirements to have that reserve energy on board. And so from a regulatory perspective, hybridization is kind of a safety valve that allows a lot of those aircraft to be applied in more situations where they can legally meet not just the certification requirements, but also the operational requirements.
And when you think about that, I wanted to ask you, when we're talking about operational requirements, have you guys done any research on the operational costs, OPEX of traditional versus hybrid versus pure electric?
Yes, absolutely.
Anything you can share, data, case studies, like where does it kind of fit in that? Because, a lot of these industries are going to be very sensitive to what those operational costs are based on the mission.
Absolutely. And we're very focused on the operating cost, cost per flight mile, cost per seat mile, all of those metrics. And what you find is if you take a convention, so I'm going to compare a conventional aircraft, one of the studies we did, we compared a conventional turbine helicopter,
okay,
a battery electric VTOL, and a hybrid electric version of that VTOL.
Okay.
And so, designed around the same mission. They were all 6-passenger aircraft, designed to fly, people from point to point. What happens, so first of all, obviously the range of the helicopter is good. The range of the hybrid electric aircraft, the VTOL, is even better than the helicopter.
Okay.
And the range of the battery electric VTOL is minimal. So there's a range comparison there. When it comes to the operating economics, the hybridized VTOL aircraft uses far less fuel than the helicopter because that's because you're bringing together a bunch of innovations. So it's the fact that you've got a winged VTOL aircraft. So it's cruising more with the efficiency of an airplane than with the efficiency of a helicopter. And the hybrid electric powertrain and the array of electric motors is what makes it practical to have the convertible flight modes, to have a winged aircraft that can take off vertically and then cruise horizontally like an airplane. So when you bring those innovations together, you wind up with a hybrid aircraft that has drastically lower fuel costs. It can be half the fuel cost per mile of the helicopter. And that's because the hybrid powertrain and the electric powertrain enable a more efficient airframe configuration. Now then you go to the battery electric version of that same exact winged VTOL, and it's a very efficient aircraft when it's moving forward. It's of course got some range challenges. One of the problems you run into is that batteries are expensive. So if you think about a Tesla, for example, and you have a catastrophic problem with the battery pack in a Tesla, replacing that Tesla battery pack can be, a $10,000 or $15,000 expense, and that's automotive.
Well, actually, here's a data point
mass-produced.
for you, Eric. A good friend of mine has, I think the second year the Model S came out. So
Yep.
his current range is literally 40 miles with a full charge.
Yep.
And to
Yep.
replace that battery pack, his quote has been $19,000. So he
that's even
just now
worse
uses
than
it
what I
for
was
short
quoting.
trips around town because he doesn't want to spend 20 grand on a new battery pack.
Right. And so with airplanes, obviously, we can't let range degrade. You can't.
Well, and also
buy a
that when the
Cessna
FAA starts
172.
certifying and inspecting it, they're not going to let you get down to that degradation point. So we actually don't even know what the cycle costs are, replacement costs. There's actually some unknowns on that side currently as far as operational costs.
Well, there are also a lot of knowns, frankly. And so let's follow that example
Yeah,
from
please.
what your friends got there, because we're going to have to derate the battery packs that go into aircraft so that you have consistent available performance from the day one that it goes into a service until you retire that battery pack. Because it's not okay to say, okay, I've got a Cessna 172 and it went out the door with 50 gallons of fuel, but every 3 months that shrinks by 1.5 gallons, and We just wouldn't deal with that for flight planning. That's not good for safety. So that battery is going to have to be replaced on a fairly frequent interval, and it's going to be based on flight cycles because it's the charge and discharge cycles that really kill a battery.
And like some of the big cars and things like that, the recommendation be, hey, only charge this to 80. Don't go above 80% unless you have a very specific exception. But now, because that actually really limits the battery life and health when you go to 100.
And furthermore, in an airplane, you can't use the bottom 20% because then your ability to pull the full rated power goes down. So you're absolutely right. You've got all of these derating things that need to happen to the battery. If you look at a perfect battery, and this is frankly how, people ask, how is it possible that people are doing these demo flights with prototype battery electric aircraft? I did some of that myself on the first electric program I worked on back in 2013. We were achieving some great flight times, but those were on brand new batteries with no derating.
I don't care about derating when I'm trying to show you my concept works.
Right. And so, yes, you can do demos, but doing that day in, day out, what you wind up with in the, people think about operating costs and they're like, well, the electricity is less than fuel. And that's true. It is cheaper to buy electricity off the grid per kilowatt hour than it is to buy fuel per kilowatt hour. But
in most states.
On most cases.
In most states, yeah.
But we're also, one of the things we also have in aviation that we all know about is you have engine reserves. Your engine needs to be overhauled every so often, and 2,000 hours, 3,000 hours or more if it's a turbine, but you've got to reserve money to overhaul that engine. There's going to be a battery overhaul or replacement reserve that has to be calculated into the cost of a battery electric aircraft. And that's what potentially kills you, because you're talking about battery packs that are many times the size of a Tesla's battery. And we already said a Tesla, I said 10 to 15,000, you said 19,000. So let's say it's 4 or 5 times the size of that battery pack. So now we're up near 100,000, and that's at automotive prices. But we all know that buying parts and engines and everything for a car versus buying parts and engines and everything for an airplane, you're talking a factor of 6, a factor of 8. I mean,
because of all the certification and the regulational requirements, and it's more expensive.
Absolutely. So it's really not $100,000 battery pack. It might be a $500,000 or an $800,000 battery pack. So we're talking about really expensive, high performance, very impressive battery packs, but that's an expensive proposition because if one of those only lasts 1,000 or 2,000 or 3,000 cycles, then just like you've got a reserve for your engine overhaul, if you're really honestly calculating what it costs to fly an airplane, you've got a reserve for the battery replacement or the battery overhaul. And that's the big cost with a battery electric aircraft. And that's one of the tough things to get past. And
that's
so
fascinating.
It's a very good question.
Yeah, and I love your examples. And, you guys are doing flight testing, I know, actively right now, and in partnership with some of your customers and yourself. And what are some key lessons that you're learning from real world flights?
So it's a really good question. And, one of the things that everyone in electrification learns sooner rather than later is about electromagnetic interference, EMI. So, we have in airplanes, you've got lots of, I would say, delicate electrical systems that are running on lower voltage and lower amounts of power, your avionics and all of those things, maybe your autopilot and your flight control systems. And then a lot of these electric aircraft, especially the vertical lift ones, there's a fly-by-wire element to that, which is really important.
Yep.
And those are mature systems and safe systems. When you put them in close proximity with hundreds of kilowatts or megawatts of power being broadcast all over the place in the airframe. Keeping the delicate, exquisite systems like the avionics systems and the computers and the control systems, keeping them happy at the same time you're keeping the, megawatt power distribution happy is a tough thing. And so, how you manage moving that power around and how you manage designing the systems that go in the aircraft, it's really important that the high voltage, high power systems don't interfere with the low voltage, low power systems.
Yeah, it's been a long time since my electromagnetic theory course, and I was an electrical engineer. You're bringing me back there,
Yep.
Eric, but this is stuff you guys are thinking
Yep.
about on how it actually works. I hadn't considered that.
Yep.
The practicality of having all these high frequencies, high voltage in proximity with each other. So just the shielding, the weight that's going to require. There's probably a number of other things I hadn't thought of.
There's a whole lot of clever engineering that goes into that. And so you were asking about kind of what's hard. The electromagnetic interference side of it, that's something you got to figure out how to address it. And we've dealt with it, but it's not easy. The other thing that I would say is the thermal management of these systems, because now you've got
in hybrid or pure battery. Is it something you're taking into account with both?
It's a little bit in both. So, but in a hybrid system particularly, we put a lot of time into designing the thermal management systems, because you've got an engine and you got to keep it cooled and happy. You've got an electric motor generator, that's got to be happy. You've got power electronics. You have a battery in the hybrid system. And all of those like to be at slightly different temperatures to be ideal. And it's easy to design a system that works. It's hard to design a system that's compact and lightweight and deals with all of that. And that's where the real innovation comes in, is how do you compress all of those things down together with really clever designs that keep all of the different elements of the system happy at the same time.
Yeah, so let me ask you this, just out of curiosity, or since 2017 when you started, what's are some of the biggest technological challenges you guys have had to solve to make this work?
So I won't talk more about EMI or thermal, but I will say those are two of them.
Those are two of the big ones, okay?
Those are two of the big ones. The other one is, the mechanical integration of all of those systems and the control of all of those systems. So you've got a whole bunch of things going on all at the same time in the aircraft, and keeping the controls on that simple so that they're certifiable.
The power controls, correct?
Exactly. The power controls on everything.
Through the whole electrical system and forward and backwards. Yep.
Well, and as much as possible, making them almost foolproof. If you can make them passive versus active in certain cases, that's really good. It requires a lot of clever engineering so that, the most reliable control system is the one that isn't there at all, because the thing just runs on its own. So if you can do that, it's hard to do, but that can also lead to some really unique designs that are very high reliability. So, I think it's really all of those things coming together.
Yeah, and then looking forward, maybe as we kind of wrap up here, let me ask you this question. If you're looking at the future of AEM, eVTOL, even unmanned drone, the whole UAS space, do you see hybrid as a transitional bridge? Or do you see this as a permanent part of this landscape?
I think it's a permanent part of the landscape, and this is one area where things are moving in the opposite direction than they did in the electric car industry. So if you look at electric cars, we started out with hybrids. I mean, and still to date, there are way more hybrid electric cars on the road than battery electric cars. Even as battery electric cars have become far more common, all the Toyota Priuses, Honda Insights, and others that were sold in the early days, we went through hybrids to get to batteries. Interestingly, in aviation, the easiest way to get an electric aircraft into test flying is to do a battery electric aircraft. The systems are relatively simple. Now, it's not terribly capable, but you can get that new airframe or new concept in the air. But then if you want to fly more aggressive missions and some of the higher value missions, you then go from batteries to hybrid, where you take this new aircraft designed around electrification, and now I want the high performance version of that. And therefore, some of the batteries come out and the hybrids go in. So I see hybrids as a long-term part of the landscape. We're talking about many decades before there's parity between battery electric, weights and performance versus hybrid electric or conventional propulsion. So, hybrid is going to be around for a long, long time. And interestingly, a lot of things are going to shift in the near term from batteries to hybrid, because either it's going to be necessary for that aircraft, or in some cases, there's a market for the battery electric aircraft, but there's also a big market for the hybrid electric version of that aircraft that can do more. And if you're an electric aircraft manufacturer, why not be able to service both markets? Once you've got a great aircraft design that leverages electric motors and power distribution in all the right ways, why not be able to deliver it both ways?
Yeah, no, I think that's a brilliant point. So, just as we end here, Eric, and I really appreciate your time and your insights, and love to have you come back as you're getting more and more to real world testing, and there's just some great information here. What are just some final thoughts as you're thinking about, the next year or two ahead, and what you're looking forward to as we wrap up?
So, what we're seeing right now is really strong momentum for the military use cases. Not to diminish anything that's going on the civilian or commercial side, because there's some really compelling things happening there too. But if we think about the history of aviation, most of the big innovations happen in the military first, and then they come over to the civilian side. And, whether that's the jet engine, turbine engine, whether that's GPS, a lot of the, avionics we use, all manner of things get matured by military use cases because they want to move faster. In some cases, they're willing to take more technology risk as an early adopter than the civilian industry. And then as things get proven there, they move over and get applied in different ways, but it's the same technologies then coming into the civilian side. So we're working in both of those areas, and we actually started out working primarily on civilian applications. But the military interest in high-performance electrification, which requires hybrids, has really accelerated over the last couple of years, and we don't see that slowing down. There are all kinds of use cases where, for runway independence, which is a big, that's a big concept for military aviation. Runways are vulnerable. So how do we get aircraft that don't need a runway? Well, we've got helicopters, we've got V-22s. The V-22 Osprey is getting up close to the limit in performance, when it comes to speed and range. You want to go beyond that. And that's where hybrid electric power comes in and gives you, the manned aircraft or the drones that give you runway independence and give our military a lot more flexibility for their next generation airplane.
Well, I think the military use case is fascinating. I think there's going to be some huge advances in that area because of some of the specific mission sets and how you're designing around that. So it's going to be exciting. So I know we're going to see some of your folks at Verticon possibly, and I know we're talking about some possible collaborations even. So Eric, it has been great to have you on, and look forward to our next conversation and meeting you in person at some point.
Absolutely. I look forward to it, and thank you for spending the time today, and love to catch up down the road. We're making rapid progress. So 6 months from now, we're going to have a whole bunch more news, a whole bunch more progress, and would love to share that with you.
Come back anytime.
Excellent. Thank you.